So I'm very excited to introduce Tegan Maharaj, who was doing her PhD at Mila with Christopher Pal, and as we just were discussing for the last couple of minutes, is joining the Faculty of Information here at UFT, and she'll be affiliated with both Vector, but also the Schwartz-Reisman. So we're very excited to learn about your work today. Take it away, and I'll monitor the chat for questions. So if you want, I can interrupt you when someone enters.
That sounds great. And I would really like to emphasize, please ask questions at any time. I love being interrupted for productive questions. I trust all of you to do a good job of that. And so yeah, really, please raise your hand, or Nicholas, interrupt me anytime.
Excellent.
I'll also try to pause for questions pretty often.
Awesome.
Cool.
Take it away then.
Yeah, so I want to convince you, well, I don't think I need to convince you that AI is currently an important component of our digital infrastructure. And therefore, we should treat it the way we treat building safe bridges. There's a lot of science and engineering and stuff about physics that we need to understand. And there's also a lot of like real world dealing with people, laws and governance and regulation and standards that we need. The pervasiveness of AI. In my time in this field, last 5 to 10 years, there's been crazy progress, and AI is now pervasive as a tool, widespread in our daily lives. And both the social systems we have for managing and regulating AI and the fundamental science for understanding how AI works have not caught up. And there's just a lot we still don't understand about how AI works and how it will perform in new situations. And that's one of my main areas of interest in research. Just to give a short example, I don't need to go through a whole lot of examples for this crowd, I don't think, but maybe a lot of you are familiar with Tay, this bot that Microsoft Research released. And nothing wrong with the bot itself, but people got a hold of it and realized that they could shift the distribution of its training data by providing it with kind of awful things to say. And PR disaster. I don't know if people were really harmed by this, but certainly it had some offensive things to say. So when we try to deal with problems like this or address them as a science, I claim we run into a lot of problems of bias in ML, and I'm going to talk about one in particular that is probably not the one that you think I'm going to talk about, and that's a bias against applied research. That's this perspective that we have that as soon as I start talking about applied research, it has the connotation of being not novel or groundbreaking. It's kind of complicated to do, but it's boring. You don't really need to be smart to do it. It's just some problem that an engineer needs to solve. Whereas pure research is like cool and exciting. Maybe it has something to do with physics or math, and it's novel and groundbreaking. You don't need to think about the real world. You need to be really smart to do it, and it's very exciting and motivating. And I know this is true for at least some people. It's true for me sometimes, but I saw this plot presented by somebody named Alan Blackwell, a cognitive scientist who works on AI, that changed my perspective about this quite a lot, and I want to convince you to change your perspective as well. And that is to view applied and pure research as these two orthogonal axes, where groundbreaking and novel research is the whole space of the positive directions. And you can think of researchers like Edison, Pester, and Bohr as being located in these quadrants respectively, where Edison is doing mostly like engineering, really applied stuff. Pester, who developed vaccines and the first methods of removing microbes from glassware, was doing pioneering pure research, but also that had very, very, very real world implications. And I want to say that responsible AI development is in this quadrant as well. Okay, an overview of what I'm going to talk about in this, like the meat of this presentation. First, I'll say a bit what I mean by responsible AI development. I'm going to go kind of blitz through a lot of my works and pause for questions after each one. I'm not going to go into detail unless somebody has questions or wants to know more, except this project that I think really sort of showcases my perspective in some directions I'm excited about, applying AI in COVID-19 epidemiology, specifically to contact trace in a private and secure way. And I'll briefly mention some of my work in policy and governance recommendations, and also applying AI to problems of climate change. And then hopefully spend a bit more time here and a lot of questions and discussion on some future directions I'm excited about, including using AI in impact assessments and for risk mitigation and risk analysis, learning ecosystem dynamics, and better dealing with or even learning from distributional shifts. And then I'll give a summary. Okay, first, what do I mean by responsible AI development? Sounds great, but what do I mean? Well, I claim that what we have in the AI development process is something like this. And deep representation learning is one wheel in this process, an important and cool component. But overall, we have a lack of understanding of basic scientific principles about like, what is this problem setting? What are the important considerations in dealing with this problem setting? We have unanticipated and poorly tested and very piecemeal solutions. Sorry, for anybody who can't see the figure very well, it's like a forklift lifting another forklift stuff up to some people who are sitting on a precarious looking beam. So yeah, unanticipated and poorly tested piecemeal solutions. Like when we developed this deep learning wheel, this is not the use case that we foresaw, I don't think most of us. And there's a lack of guidelines and oversight, really self-regulation, and no comprehensive human-centered regulation. So what should we do about that? We need foundational science like learning theory, just empirical understanding of the methods we're using. We need multidisciplinary collaboration to identify the ways and problem settings in which AI can be usefully deployed. We need methods of testing and evaluating AI systems before they're deployed in the real world, and that's an area I'm pretty excited about. And we need norms, standards, and governance. So my research, unsurprisingly, I've presented all these problems. I addressed all these problems. That's how these slideshows work. As I said, there's a lot we don't understand about how AI works, and what I want to do to address that is methods and like an overall very empirical approach, but basically modeling more of the real world. So we have this learning setup where we usually conceive of there being input, the model, and the output, and anything else is maybe distributional shift or violation of the assumptions that we don't think about that much. And of course, it's not computationally feasible to model the entire real world to a high level of fidelity, but we can do better. We can model more aspects of the world and the ways they affect learning systems, for instance, distributional shift, or the kinds of more structured output or continual learning type learning settings that are different from our supervised learning setups. And some things I'm interested here are dealing with and making use of distributional shifts and average case or realistic case generalization bounds. So of course, AI is useful for stuff or we wouldn't all be here. And some of the use cases I'm most interested in include sociological and environmental problems, like problems of climate change. And I'm really excited about using predictive models in impact assessments. So an impact assessment or a risk assessment is like there's some scenario. This is usually modeled by a bunch of people in a room talking about like, okay, what's going to happen if we build a bridge here or knock down this factory or pollute this river. And predictive models are used somewhat, but it's like, linear regression on a few variables that have been collected that are presented to some kind of working group that then move through this in a more qualitative way. And I think there's really a space, especially in these very high dimensional problems where inference alone of like what is going to happen, that's a challenging research problem. We don't know how to do that. Going from a really high dimensional statistical model, like a climate model that we have, to forecast ground level, for instance, weather patterns. And in general, I would say deep learning, representation learning, really helpful in this kind of problem where we have some kind of high level statistical model that is relatively well understood, but we need to make individual level inferences, particularly if we have like privacy concerns or other computational concerns that make like analytical solutions infeasible. And lastly, I've mentioned this a couple times already, we just need some regulation and standards, third-party auditing, and more widespread responsible standards for AI. So let's get started into the meat. Actually, sorry, I've been remiss in not pausing so far, but are there any questions, comments?
Not in the chat so far.
Okay, haven't really got into like the meat of the presentation so far. So my work, the first couple works that really got me into this line of kind of empirical analysis of learning behavior were these big group projects we started at Mila on looking at memorization in deep networks. And the main takeaway from these papers is that learning and memorization, so like memorizing behavior versus generalization behavior, depend on the data distribution. And maybe that seems obvious at this point, several years later, but, and it was, most folk wisdom at that point, but we demonstrate through a series of empirical experiments that this is the case. Anybody like more detail, go into this more, questions?
Yeah, I would be curious if you can give more details.
Yeah, didn't think too much about how to do this smoothly, but let me unskip these. So the sort of key experiment that we did is the overall approach that we did is to operationalize the definition of memorization as whatever the deep network must have done to fit random data, because random data has no patterns, has nothing that could be learned and generalized from. So in all these experiments, we're comparing behavior on random data to real data. And these differently colored lines here are different amounts of noise. So the real data, I think these are CFAR, and the noise, X noise means that it's data noise. So it's uniform randomly sampled pixels are replaced with like 0 to 255. And as you can see, with increasing amounts of noise, of course, validation accuracy goes down, but over the course of training, there's this jump very consistently before overfitting occurs. So there's this validation spike where the networks are first learning these patterns that generalize well before overfitting. Does that make sense? And these different, oops, sorry, the different plots are different data set sizes, I believe. Another cool result that I really liked is this experiment about easy examples that David Kruger ran. And on the left, this is showing for a feed-forward network, and on the right, this is a recurrent neural network. Do you see my mouse, by the way?
Yes, we can see it. I always wonder that too.
Yeah. So the red line here is rand X, that's what I described, where the input pixels are randomly replaced with noise. Rand Y is the labels are shuffled. So randomly selected label, but the input image is data. And what you see here is that when you have normal CFAR, the distribution of easy examples, the probability of getting an individual example correct in the first epoch, I think this is the 5th epoch, but like first couple epochs of training, is sort of evenly distributed across the data set. However, if we have random data for both kinds of random data, what I want to say about evenly distributed, like there are some examples that are really easy, that are almost always classified correctly within the first epoch. And there are some examples that are consistently hard. Like there are patterns in which examples are easy and hard for the real data. Whereas for the random data, this is just following, it's random whether or not the example is easy or hard to classify. So this shows that in real data, there are patterns that can be picked up on to generalize better. And this is just showing that it's also the case for recurrent neural networks, but we have this interesting like different shape of like there are more easy examples. Yeah, but we didn't really have anything super insightful to say about that. It is interesting.
What's the x-axis on this graph?
The probability of getting correct. So like sorry, you said x-axis?
Yeah.
The number of times that example is correctly classified within the first epoch.
Okay.
This is a histogram basically of easiness of examples.
Right. Okay. Thanks.
No problem. Yeah. Any more questions about this paper? There are a lot of plots. I only chose these two to go into detail about. Some other cool results from there that were followed up on a lot by Stanislaw Jastrzębski and other people are how different types of regularization affect memorization behavior. And the TLDR there is that dropout and related techniques like ensembling are most effective at reducing memorization behavior. So that was neat. Another paper around the same time that also takes an empirical approach, but is looking at video fill in the blank question answering. Took this really simple approach of there's a large annotated data set called the Large Scale Movie Description Challenge. And captioning for images with MS COCO had recently become a really popular and successful benchmark. But we tried those models basically for video and found that they performed really poorly. So we were looking for an auxiliary task that would let us understand better what was going on, why was the performance so poor for video models. And we came up with this benchmark. The way of making this benchmark was just to randomly blank out nouns, adjectives, and adverbs in the descriptions and have the model fill them in. So this was inspired by work in word embeddings like skip thought vectors. And we perform a lot of analysis of the results of how good how performance on this data set correlates with human judgment of quality of captions and sort of why you would expect filling in the blank to be a helpful auxiliary task. So yeah, some takeaways are that some simple predictive tasks can really improve the representation. And by doing this human evaluation, we can design better evaluation metrics, for instance, based on query tasks like this, rather than based on like BLA or word overlap scores that are really not very indicative of what we actually care about.
So here in the, is this similar to what people are doing in, I guess, like semi-supervised learning or?
Yeah, so this is actually like, this is masking. This is language masking. This is before BERT. This is the year before BERT came out. So like, I guess the idea was in the air sort of.
Yeah.
But yeah, it's like any argument you have about why masked language models have been successful, that's like, we explored a little bit of that in this paper, but it really took off the year or two after.
There's also a question in the chat from Shaitanya who's asking, were there any examples which were initially easy, correctly classified during the initial epochs, but later turned out to be hard?
Yeah, so this is a really interesting, I don't know, I think it's really interesting sort of field of study is looking at which examples are hard when, and when, Stan had a term for this, like when the accuracy flips, so like when you start making mistakes that you didn't make before over the course of training. As far as I remember from results, at least on CFAR, usually the easiest examples never become hard, but there's like activity in the middle, and it's interesting to see sometimes what the network is like learning currently by looking at which examples flip from being correctly to not correctly classified. One of the contributions of the memgen memorization and generalization works was a measure of that is sort of based on that, a measure of complexity of the loss surface that we called the critical sample ratio. So that measures in output space how many in a box around the ground truth answer, how many examples are classified differently. It's related to something Ian Goodfellow did with adversarial examples. It's sort of measuring how rough the loss surface is, basically. Like, if you had a similar example, how likely is it to have a different classification from the current example? And yeah, there's some cool plots in there about relating the critical sample ratio to how much memorization and generalization behavior you have. And there's this whole thing about sharp minima that people were interested in for a little while that came out of that.
Excellent. That answers the question. Feel free to ask a follow-up in the chat, and I'll interrupt again.
Yeah.
All right. I think that's it for now.
Cool. Another empirical work from around this time. So we looked at the success of methods like dropout, but I was very interested in temporal data. And the regularizers for RNNs at that time didn't work with dropout because dropout introduces zeros in the transition matrix. So you end up with vanishing or exploding gradients. And we came up instead with this method called zone out, which instead of introducing zeros in the transition matrix, introduces the identity operation. So the idea is pretty simple. It's just instead of zeroing out individual activations, you set them to their previous value from the previous time step. And basically this worked really well. At this time, RNNs had like really wide industry application for speech and even NLP still. So this was like a useful technique. These days, RNNs aren't being used as much, so it doesn't see as much application, but yeah, just a simple idea that worked really well. And we showed that the randomness is good for robustness, all like basically by the same arguments that dropout is. And also we showed that the identity connections preserve information flow through time even better than an LSTM does by having these identity connections. Any questions about that?
Not that I can see.
Cool. This is very recent work with David Kruger, who was an intern at DeepMind with Jan Leike at the time. And the title is a bit of a mouthful. Does under-specification incentivize auto-induced distributional shift, a unit testing approach? So we define this idea of auto-induced distributional shift. That's distributional shift caused by the presence or actions of an algorithm. And basically the answer to this question is yes. We claim that by not taking into account the effects that an algorithm might have, specifically we look at a toy setting that is sort of like a prisoner's dilemma, and more concretely at a toy environment of a content recommendation setting. So if you don't take into account the auto-induced distributional shift of the recommender system, you will end up with drift in user preferences or in the user base. So these model real-world effects, like let's say driving users away from a platform by polarizing their views, or by manipulating users by changing their interests due to due to what you show. This is called a combination of the illusory truth effect, which is like if you're told something, you're more likely to believe it is true, even even for pretty ridiculous statements, and like a sort of groupthink effect. I forget what the exact term is. And the approach that we took to dealing with this is to say, well, we don't know in advance how to specify that we want the recommender system to show good articles without manipulating users in this way. However, we do know how to test for it afterwards by testing for distributional shift. So we make a unit test environment where you can deploy an algorithm that you're thinking of using for content recommendation, for instance. And there's a more general, like I said, a small environment based on the prisoner's dilemma that is a more generic test. So you can use that unit test on your algorithm. If that algorithm fails the unit test, that is evidence that in practice, the algorithm may achieve its performance by causing distributional shift, not necessarily by the means that you wanted it to. So I'm really excited about this approach in general for hard to specify behaviors, testing for them in like simulation before deployment. Any questions about that?
I guess, do you think have you thought about other properties that may be hard to specify that could benefit from this type of approach? Because it's true that there's a lot of things, I guess, that I think could, like in like responsible AI, that could be relevant to this type of approach.
I've thought about other applications of distributional shift, so like self-driving cars, autonomous robots, that kind of thing. The main other area off the top of my head is privacy and privacy violations, and also more generally like violations of regulation. If you had some way to translate a regulation into, like, I don't know, let's say an amount of CO2 that is released, or some other metric that is easy to measure in the real world, or in simulation, then you can measure how much the algorithm causes that thing to happen, yeah, and test for it.
Makes sense.
I would say the adversarial examples community is sort of doing this approach to a large degree, but not calling it like unit testing or sandboxing.
Yeah, I think it's also different properties that people are looking at, but yeah.
Yeah, mostly thought about distributional shift, because it's like, it's not obvious that there is a way to test for it. But I think the work David and Jan did, and then I helped out, I think it works, it's cool. Basically, so the way the small environment works is to make a POM-DP where the actions of the algorithm are played against its past self. So in a very abstract general way, anything that you can think of as a POM-DP, you could turn into a unit test in a similar way. Okay, so that was sort of the whole section on these empirical ways of understanding learning behavior. Now I'll talk about a couple more applied projects. This first one was the first work accepted that I know of to a major ML conference that dealt with the problem of climate change, and we were recognizing extreme weather events in large-scale climate data. This was at NeurIPS in 2017. And basically what we did was have a large-scale physics model run on a supercomputer that generated these images, or more like videos, of the climate over an 80-year period, where instead of channels like RGB in a normal video, the channels are things like temperature or pressure or water vapor, features that are useful for predicting climate events. And then we used a climate toolkit called Tegan to label extreme weather events in that climate data. So this is a heuristic based on like expert knowledge about, like, if the temperature and pressure is above this and it's been more than 3 days, label this as a hurricane, things like that. And then we used that as ground truth, trained a deep 3D convolutional autoencoder in a semi-supervised way, because we didn't have Tegan, the toolkit, we didn't have labels for every image. And basically we found that the deep learning model was able to do a really good job of recognizing hurricanes, not so much other types of extreme weather events. And we also, in using the bounding box regression methods of the era, combined a few of them and made some tweaks, and had a bounding box regression method that worked better than other methods, because we actually dug into things like, wait, what is the effective receptive field when you start out with, this method? And some of our hacks and tricks to make that better became widespread in bounding box regression methods. But the cool thing I found about this was just sort of getting the word out there about working on climate problems to the mainstream ML community. Any questions about that data?
There's nothing on the chat.
Cool. In a similar vein, a couple of years later, I was part of this big multi-institution report on tackling climate change with machine learning. And that has now, a few years later, turned into this organization, which will soon be a 501c3 charity in the US and starting a multi-million-dollar grants program called Climate Change AI. And this paper, I authored one of the chapters in it called Collective Decisions. The way the paper works is that if you're a machine learning researcher, you look at the columns at the top there. Sorry, it's hidden by the video for me, but like causal inference, computer vision, choose your area, and then look down where there's a dot, go over and read that area. Like if you're into interpretable models, maybe there's some cool stuff you could help with in forecasting extreme events or modeling social interactions. So that paper was pretty, I don't know, successful. And the main takeaway we wanted to push is that ML is not a silver bullet. We don't want to say that like we can solve climate change with machine learning, guys. You can relax. No need to worry about the climate crisis. However, there are ways that ML can be usefully applied, and we want to direct the field towards those ways that it can potentially be useful.
Did you also discuss the implications of ML on climate change?
Not so much in this paper. Climate Change AI does have, we have like a webinar series on that. I think we have one chapter about, or like a section in the introduction about the climate impact of AI and how to deal with it. Relative to most of the large emission sources, scientific computing is not huge. And the other effects of AI on climate change are sort of like really downstream counterfactual things that are hard to measure. There are some people in Climate Change AI working on a follow-up report that is just about that. Like, how can we forecast the impact of AI in the climate sector? But this is focusing on like existing technologies, existing things and ways to like things that have the highest pathway to impact, where AI can be like, there's a reasonably high degree of certainty that AI can be like usefully and responsibly applied.
Awesome, thank you.
No problem. And finally, this is one that I'm going to spend a little more time on because it brings together a few things from my work that I think are cool. And that's, we started this at the beginning of the pandemic, predicting infectiousness for proactive contact tracing. This is a multi-author, co-first author paper. We were doing like, I don't know, 16-hour days at the beginning of the pandemic because we thought this was maybe going to become the contact tracing app for Canada. Like Joshua met with the Prime Minister and stuff like that. So it was always like, yeah, next week we need to have this plot ready and stuff. And that didn't happen for a variety of reasons that were very good lessons in, you know, doing science in the real world. But I think a lot of our methodologies are still really useful for doing science in the real world, a lot of good lessons. And I'm very happy with this project. So just to back up a little bit, in case you don't know what contact tracing is, manual contact tracing is where you like phone or email known contacts once somebody has been diagnosed positive with the disease and tell them to quarantine. And this works quite well in relatively small epidemics, but it was overwhelmed largely by the scale of our pandemic. And so digital contact tracing in the last few years, even for the previous MERS epidemic, supplements manual contact tracing with a smartphone app that automatically alerts any contacts that you've been within Bluetooth or Wi-Fi range and tells them to quarantine. So the existing approaches prior to our work, we call binary contact tracing because they work on binary information, a positive or negative test, and they make a binary recommendation to full quarantine or nothing. And basically we looked at the situation and we said, we can do better with deep learning. We can aggregate weak individual level features to produce graded risks that are non-binary. And that could allow people to make more informed decisions about how to manage their own risk. And the key, one of the key challenges here is to do this while preserving privacy. It's a really big concern for any app technology, but also given the nature of an epidemic. Okay, so overall, how did this work? We have each person in this diagram having on a smartphone, And on their smartphone, they have an app that has pre-trained predictor, trained offline, which takes in these individual level features, including risk from contacts, any self-reported symptoms they've had in the last few days, any test results that have been registered by them or central testing agency, any pre-existing medical conditions. Those inputs go into the predictor, and the predictor predicts an individual level risk. And that risk is quantized and sent as a risk message to other contacts. Oh, sorry. Okay, I had a lot of, yeah. So estimating all these individual level infectious risks is a distributed inference problem that would be easy if we just centrally stored the contact graph and had the ability to have a high bandwidth of contact between nodes, where nodes are people's individual smartphones. But those aren't possible due to privacy and just logistical concerns. You'll run down the battery of a smartphone pretty fast doing multiple iterations of like loopy belief propagation or something. So how do we solve that problem? As I said, it's to train the predictor offline. But how do we train a predictor offline on data that like doesn't exist about the epidemic? Oh, sorry. Yeah, we addressed the privacy concerns by quantized messages. We used a set value transformer for the predictor, which the privacy concern there is you could identify somebody by the ordering of risks they received, or by the if the quantized messages, if the messages were not quantized, you could identify somebody by their risk. And if you could look at the time that messages were sent, and let's say you only met one person that day, and the risk message was sent immediately after you met them, you could identify that person. So we batch all of the risk updates into certain periods of the day, and then to deal with the set valued nature of the input that we have now, where contacts are not temporally ordered, we needed to use a set value transformer. And then in order to train the predictor, we developed a detailed epidemiological simulator in collaboration with doctors and epidemiologists and virologists, and trained the predictor from simulated data.
Could you explain how you reason about the privacy here? Like what definition of privacy are you using to basically define what is acceptable to transmit?
Yeah. We had a cryptologist from from McGill. So basically it's what he thought was appropriate, and it's 16 levels, like it's quantized to 16 levels. I forget what like the probability is that you would be able to identify somebody with that. But I think in a population of over 1,000, it's like vanishingly low. But I don't know the name of the framework that would be.
I see. It's based on some re-identification estimates.
Yeah.
So you haven't considered things like differential privacy or to reason?
We have we don't need to do anything differentially private, because the predictor is like pre-trained offline and only lives on your phone. So no personal information ever needs to leave the phone. We would need to deal with differential privacy if we wanted to, which we did want to, give the opt-in option to give your data to improve the simulator. But for the first version of the app, we were only using pre-trained predictors offline. Your data never leaves the phone.
But you still share some information between phones, right?
Risk messages, yeah. So
those contain information that is derived from private information?
Yes. So the only way we deal with, there's no differentially private thing there. The only thing we do is quantize the messages and batch the sending to 4 times per day.
I see. Okay.
Any other questions about the approach? I'm going to go into some more detail about how we actually train the predictor.
A question from Surush, who was asking, did you look into federated learning to improve the predictor over time?
We did. We started to do that and look at variational approaches versus a graph neural network approach. Basically, we focused for I don't know, the interest of deployment on making something that we were sure would be private enough to be like sort of usefully deployed. And the issue with something like that is you need to do, you need to have you need to have privacy guarantees that the government is happy with for the way you collect the data. And we did have a data trust set up that would do that, but because we weren't, because we didn't end up being the app that was actually selected, we didn't have the real data to do some of these variational approaches, so we didn't explore that further. Because like the experiments that we ran were like simulating the real data that we might get and trying out the variational approach to see if it would work. And like it worked decently well, but how much are we really saying if it's like simulation all the way down?
He says thank you.
Welcome. So yeah, on the subject of simulation all the way down, we have what's called in epidemiology an agent-based simulation. So there are sort of two broad classes of epidemiological model. There's statistical level, where you predict how many people in the population will be at any time infected or recovered, for instance. And agent-based simulations, which model individual like agents moving around and their behavior, like going to the grocery store or whatever. And we used an agent-based simulation because that allows us to produce these individual level features, and also really importantly, individual level latent variables like infectiousness and viral load. I'm getting a little low on time and I want to leave time for questions. So I'm going to skip through some of the details. Basically, we domain randomized over simulation parameters and to have a robust model. And there's distributional shift caused by the prediction. You'll see a different patterns of disease once you start recommending that people stop going to the grocery store, for instance. So the algorithm causes distributional shift in the simulation. And the way we mitigate that is to iteratively retrain. So like it's sort of a brute force approach, but to produce new simulations, put the ML model back in the loop of the simulator, produce more data, train on that data, and repeat. Okay, and does it work practically speaking? Basically, yes. Sorry, I'll go back one, but the green ones here are the deep learning based methods. This is the cumulative cases over time. This is no tracing. These are some baselines, the pink and yellow. And basically, they reduce cases much better. You can see on this side. And in measuring the amount of change to behavior, PCT, proactive contact tracing, the deep learning-based methods, barely require quarantines more than no tracing does, whereas binary contact tracing and the other baselines we tried achieve good performance in reducing cases, but they do it by quarantining a lot of people unnecessarily, and that can lead to like pandemic fatigue and just, sucks. Okay, yes, so takeaways: deep models can aggregate weak signals to make good predictions, and pre-trained models allow for private distributed inference. And I'm going to skip through this. This is a report that I was on about verifiable claims. There are 10 concrete recommendations, including safe bias and safety bounties, red teaming, third-party auditing, reporting of like bad behavior or AI incidents. So yeah, take a look. And I want to talk really quickly about some future directions and then have some discussion and questions about those. So I've mentioned, sorry, maybe any questions on the COVID work or the trustworthy AI work before I go on?
Tegan, quick question for you.
Yeah.
You mentioned that you learned a lot of working in the real world setting lessons that you've learned out of the COVID work. Do you want to share some of them with us?
Yeah, we had this very, in retrospect, naive idea that we just needed to show convincingly that it works, and that was the big challenge. But once we did that, it really works better than other methods of contact tracing. But that's not, you're not done just because it works. So there's a lot of one of the main reasons I think that our method wasn't selected for the app is that you need to communicate about what is going on to policymakers. And there was, it was open source from the beginning, and there was some like controversy online. I don't know if you guys remember at the beginning of the pandemic, people were very concerned about these contact tracing apps and Big Brother and all this stuff. So we were very open about the whole development process and saying that we were like developing a privacy first design and talking about like we had, went on TV and stuff, the crypto analysis person from McGill to talk about how the privacy stuff worked. But anyway, we had like controversy around it basically. And the apps that they selected eventually had been developed in-house in a private company, and there was no controversy surrounding it. So like, I tend to have this bias, like, yeah, just be transparent and open and discuss things. And like, yeah, there could be problems, but let's talk about it. But it's not always the right way to do it. And I don't necessarily know what the solution to that is, but it's a hard problem.
Thank you. That's really interesting. I'm gonna kind of pass it back to you for the rest of it and maybe chat about it sometime later. Thanks.
Yeah, sure. Happy to. So yeah, I mentioned using this sort of overall approach for impact assessments. To be concrete about what I mean, this is the approach that I mentioned for COVID-19, where you have like the risk level contacts and symptoms and individual level characteristics going into the deep learning model. But I'm interested in using this for other kinds of settings where we have different risks that we want to predict from some high level, well understood statistical maybe model, in order to reduce some distributed risk, like the effects of climate change. So for instance, you can imagine pricing carbon this way, or instituting a carbon tax, where the features might be things like individual org characteristics and the amount of CO2 they produce. Here, the agents are not individual people. It might be something like an industry or a particular factory. And then, yeah, the associated recommendations or tax or whatever will cause shift in the data that then needs to be dealt with in a similar way to what I discussed. Another example that is very similar is pricing negative externalities or setting fines or something that a company has to do as a result of producing negative externalities like pollution. So I think this overall approach of designing an agent-based simulation in cooperation with like domain experts, training a deep learning model to predict individual latent variables, and then using that to predict a risk or a score that can be converted into a tax to change behavior for in order to achieve a desired outcome, like reduction in risk. I'm excited about that for impact assessment. Another project that I was actually working on before this whole COVID thing is learned ecosystem dynamics. So ecosystems are often modeled with ordinary or partial differential equation models that describe, like, you have the rabbit population going down as foxes eat them, and then the fox population starts to crash as there aren't enough rabbits to support the population. You get these maybe stable limit cycles or population crashes. And for more complicated ecosystems, in order to perform impact assessments or like use these models in practice for making decisions about, for instance, conserving biodiversity, there's a lot of computation involved, a lot of expert knowledge. And like maybe seems obvious to a deep learning audience that there are commonalities in the dynamics of ecosystems that could be learned. So what I was doing was creating this metadata set by using differential solvers on different ecosystem models and just trying out different representation learning methods, seeing what works well, with the end goal of using that to perform ecological impact assessments. And also just looking at like distributional shift and like how does meta learning compare to like non-meta learning approaches for this kind of data. And finally, something that I'm interested in doing is, and I've seen some people have this idea, is basically, designing generalization suites of different validation sets. So instead of having just one test set, you have different test sets that, for instance, have different amounts of distributional shift or have different key properties, sort of like a unit test, but it's just a test set. It's just the data has been engineered to test for a particular performance on a particular type of data. And that can both tell us a lot about learning behavior, could form part of like a practical auditing suite for like deep learning systems in practice. And maybe also, once we have these suites, we can actually learn features of the distributional shifts that are realistic in practice and use that to develop better average case generalization bounds. And I've mentioned unit tests already. We sort of talked about this in the middle of the presentation, so I won't go into it. Sandboxing is what I'm calling like what we did in the COVID project, where we put the AI system, the deep learning predictor, into the loop of the simulator to see what distributional shift it would cause. And then that allowed us to deal with the effects of the distributional shift and like observe that our iterative retraining process was working. But that is like a pretty brute force approach, as I said. It seems stupid and wasteful. It's very computationally expensive. So I think there's a lot of work that could be done to do that better and develop better strategies for dealing with that self-induced distributional shift. And in general, having a sandbox like this is a really useful step before RCTs, where we can determine what RCT we want to do that would be most helpful, even in a information theoretic sense, what would give us the most information about our latent variable model, for instance. So yeah, those are all things that I'm excited about. In general, a lot of these things I think fall under the umbrella of reliability engineering for AI systems. So that's a term, I don't know, I might try to push in future. And in summary, this is very like, please hire me slide, but this summarizes my, my goal is to build this like scientific foundation for understanding AI behavior and testing AI systems in practice before we actually use them, because I think we need to do more of that. Thanks very much, everyone. Please ask questions.
Thank you, Tegan. So I don't see any questions in the chat. Does anybody have additional questions that they want to ask? You can unmute yourself, I think. I have to go in 2 minutes, so I'm gonna drop out, but I already asked questions during the talk.
Yeah, I appreciate it.
So I have maybe one question for you, Tegan. It's kind of related to the question you answered earlier about lessons learned from the COVID project, but I'm thinking of it from a slightly different angle, which is I like that a number of the different projects you've presented have potential like policy ramifications, and you might imagine that policymakers will be among the readership of your papers. I'm just like kind of wondering if you have any reflections on like presenting a paper at NeurIPS that also might be read by policymakers. Like how does that change? Yeah, language. Like how does that change the presentation and that sort of thing?
Yeah, great general question. It's something I've sort of spent a long time thinking about in a not very concrete way. But so this paper, the proactive tracing was presented in ICLR oral, but we have like another paper that is focused on the agent-based model simulator, developing that simulator, working with behavioral scientists to develop the recommendations that would be likely to actually, have people follow them. App design people who like design the interface so that it would be friendly to use, make people more likely to use it. It's like an onion. The more and more you peel away, the more and more interdisciplinary like problems you encounter. For policy in particular, I would say a big shift. Actually, this is not just policy, but in general, is like make sure everybody knows what you mean when you say model. Not everybody has a different idea of what the word model means, and conversations where we have clarified that at the beginning and talked about it kind of at length have gone much better. For most social scientists and policy people, a model is like an overall approach or a qualitative way of thinking about something, and it's very unintuitive to them to think about model as being like a neural network architecture. So there are probably other examples of language that you should just like censor yourself, basically. Don't use it or explain it if you do in conversations. But an overall recommendation would just be having a lot of those conversations at a pretty detailed level I think it was ideal being a grad student on this project because I was mostly interacting with other grad students. And I think, I don't know, that's a good mindset to be in for like, oh, I don't know your language, you don't know my language, but both doing cool research. Let's like talk about it and ask a lot of questions, even if like, I just didn't understand this word, even though it's an English word and we both speak English, like, let's talk about that word for 20 minutes.
Thanks, yeah, helpful.
I would say also, like, it's better just to find collaborators and trust that you trust rather than try to learn another language yourself. Like, I wouldn't try to write a first author policy paper.
So Nicola had to drop off, but does anyone have any other questions?
Yeah, I have a question about your ecosystem future work and basically how you think that will, because I'm assuming you're thinking climate change is a part of that and modeling climate change is a part of that. How do you see that going, or what do you hope to do there?
The main two things I'd like to do are the two things that I mentioned really briefly at the end is pricing carbon for particularly, let's say in a city, model the different, I don't know, like the transport industry, different factories, et cetera, and their carbon production, and be able to assign like individual level costs that would reflect their carbon contributions, carbon equivalents. And the other one that is more broad is, in ecology is pricing negative externalities. I think it's just such a general problem that there are people doing shitty things in the world that have no consequences for them, but they're causing harm to such broad swaths of people. And we need mechanisms to, like, the first step is just to quantify that harm so that then you can at least tell people like, hey, you're causing 300 million suffering today. And then I think that's a good like first step, but also like translating that into real regulatory pressure or monetary losses, I think is the next step.
Thank you. Another thing I wanted to talk about later.
Yeah.
Does anyone have any other questions? No, we've gone a little over time, so we can probably wrap it up here. Thank you, Tegan, for giving such an interesting talk, and thank you to everyone for attending. I hope everyone has a great weekend. Oh, a long weekend, a good long weekend if you're in Ontario.
Yeah, thanks everybody for coming before the long weekend. Hope you have a great vacation.
Thank you again. Bye. I'm waving. You can't see because I have my camera off.